Okay, thank you very much. So first of all, let me thank the organizers and the KTP for hosting this interesting conference. I am not quite at the KTP, but just 1 mile away. In this talk, I will describe work that I've done with 2 students at Perimeter, Diego Del Mastro and Matthew Yu. And I won't have that much time to say too much about this, but I will mention a few things that we have done since then. All right, so a central theme in physics, and one that transcends essentially all disciplines, is to determine what is the low energy dynamics that emerges given a microscopic Hamiltonian and a microscopic set of degrees of freedom. It is the fact that what can emerge in the infrared at low energies that looks radically different to what we put in the ultraviolet is what makes physics extremely rich. The first qualitative question that you would want to know, given a microscopic Hamiltonian and a set of degrees of freedom, is to determine whether the spectrum is gapped or gapless, namely if there's a gap in the energy spectrum, okay, in the thermodynamic limit, as this will have drastic consequences for the large distance behavior of the theory. Okay. Now, asking these questions is simple to state, but actually answering these questions is usually a non-perturbative problem and hard to answer. And in general, we do not really have the tools to determine whether a particular model is gapped or gapless. A beautiful example of a theory in which what emerges in the infrared looks radically different from what you put in the ultraviolet is Yang-Mills theory. So Yang-Mills theory, which is described by this famous Lagrangian and the space-time dimension, is a theory that at short distance is constructed out of massless gluons, but it is believed non-perturbatively to develop a mass gap. And this is a prime example of a theory that what you see in the infrared is different than what you put in the ultraviolet. In this talk, we will try to generalize this theory to a very large class of theories, which will be to couple Yang-Mills theory to dynamical massless quarks in a representation R of the Gates group. So this defines a very large class set of theories, some of them very relevant for nature. And the kind of question that we would love to know the answer to are here are some of the following questions that we would like to know the answer to. Okay. So we would like to know which QCD theories in dimension n are gapped and which are gapless. Namely, one thing that we would like to know is, given a quark content of your QCD theory, is this theory gapped or gapless? Can we make a list of which theories are of one type or the other? Okay. That's one question. Another more quantitative question would be, given that you have figured out which ones are gapped or gapless, can we determine what the low energy description is? Namely, is this some conformal field theory that describes some gapless phase, or it's some, for example, topological field theory that describes a massive phase? Okay. So this, of course, we're very far from having a complete answer to this question, but let me mention what we know in some of the things that we know in various dimensions. So in 4 dimensions, let's say QCD in 4 dimensions. One important property of QCD in 4 dimensions is that asymptotic freedom bounds which QCD theories can be gapless, simply because if you put too much matter into the theory will be infrared free and you have massless particles in the infrared. Okay. So we know that at the very least the set of theories that can be gapped is bounded. Okay. And it was found many years ago that instance of a theory where you add some quarks in which the theory still remains gapped. So we know that if you have too many quarks, the theory is gapless. We know that if you have no quarks, the theory is gapped, or at least believe that it's gapped. That's just the Yang-Mills conjecture. And it's known that if you put a quark in the adjoint representation, the theory is gapped. And the theory has a fine n vacua, if you're looking at the SUN, with a trivially gapped vacua in adjoint QCD in 3+1 dimensions. Of course, we do not know in general which 4-dimensional QCD theories are gapped and which are gapless, which are gapped in particular.
Excuse me, if quarks are exactly massless, then the theory is not gapped because pions are massless too, right?
Sorry, this is n equals 1 super Yang-Mills.
If you have exactly massless quark, dynamical massless quark in any more or less in any representation of G, because the pions are massless, this theory is not gapped.
There is no flavor symmetry in this theory.
No, you wrote in your line number 4, QCD and theories, sorry, number 3, QCD and with dynamical massless quarks, right?
Yes. Yeah, but it could be one flavor of quark in a representation R.
Ah, okay.
That's what I mean. Yeah. Of course. Yeah. So this example of a joint QCD is Yang-Mills theory with one flavor of quarks in the adjoint representation. Are we okay?
Yes.
Okay. Okay, so now we can ask a similar question in 3 space-time dimensions. So this is very interesting from many points of view, including questions in condensed matter. One thing that has, there's a beautiful expansion that was developed many years ago, where one can reliably establish that, well, one important difference in 3 dimensions to compare to 4 dimensions is that the theory is supranormalizable, and any quark content that you choose, the theory is strongly coupled in infrared. So a priori, there is no bound on which theories can be gapped in 3 dimensions. And in fact, it was shown in QCD using the large representation expansion, sometimes it's called the large NF expansion also, that any QCD theory with a large, in a large representation expansion flows to a conformal field theory. So an important question was to ask whether, so for large representations, again, we know that the theory is gapless. We know for no quarks, the theory is gapped. Does there exist theories that are actually gapped in 3 dimensions? And in more recent times, it was argued that indeed such gapped QCD theories exist in 3 dimensions, 3 space-time dimensions. So let me give you one characteristic example of a theory that actually is gapped in 2+1 dimensions. So consider actually SG2 Yang-Mills with one quark in the adjoint representation. Now, this theory flows in the infrared. It was, I mean, I'm not going to go through, there is a lot of details I'm skipping here, but I'll just tell you what the answer is, what the believed answer is. This theory flows to a gapped theory described by a topological quantum field theory, which is this U1 level 2 Chern-Simons theory that plays a very important role in the quantum Hall effect. Okay. So this theory is gapped because it's described by this topological quantum field theory. This phenomenon is quite interesting because you started with a collection of SG2 Gates fields, but in the infrared you get emergent Gates fields with the U1 Gates group. This theory, Chern-Simons theory, famously has anyons, emergent anyons, and one surprising property of this theory is that this theory exhibits quark confinement. Now, this is a bit surprising because this theory has dynamical quarks that are in the adjoint representation. So you may wonder who broke the string, okay? And I don't have too much time to explain in detail how this works out, but a physical picture of how the confinement occurs in a theory that has no quarks charged under the center is that actually this theory has certain monopole operators that carry a spin 1/2 and therefore screen the charge under the center that can end on a line like a Dirac string that generates the center symmetry of SG2 adjoint QCD. So it is the existence of this monopole operator that transforms in the fundamental representation of SG2 that is responsible for the breaking of responsible for the confinement. So while explicit examples of gap QCD theories were found in 2+1 dimensions, we are very far from having a complete understanding or complete list of what are the gap QCD theories in 3 dimensions. So in this talk, I will discuss the following questions, which actually can be completely solved, which will be which QCD theories in 2 space-time dimensions are gapped and which ones are gapless, and the second question, so the first question is something that we will be able to rigorously prove. The second question will involve some guesswork about infrared dynamics. But the second question will be what description do we have in the infrared? Specifically, if the theory is gapped, we will want to know which topological quantum field theory describes the gap phase. And if the theory is gapless, which conformal field theory emerges in the infrared? So this is what I want to try to tackle in this talk. Okay, so let me very quickly tell you about 2-dimensional QCD. So QCD with Gates group G QCD in 2+1 dimensions is specified by a gauge group and a pair of representations for the left and right moving quarks. Notice that this is radically different than in 4 dimensions, where I can always write a QCD theory with just using the left chiral quarks. That's not true in 2 dimensions because complex conjugation does not flip chirality. So I have to specify a pair of representations of the quarks. Okay. Now this theory has all kinds of and I'm going to be discussing for almost all the talk massless quarks always. So this theory has a whole bunch of symmetries. I've here listed a few of them that will be somewhat important for the rest of the talk. And one that will come back to it soon is the fact that this theory can have a one-form symmetry, sometimes called the center symmetry, which essentially is the subgroup of the center that's not screened by the dynamical quarks. Okay. One way to think about that I find useful to think about this is that this QCD theory can be obtained by gauging a subgroup of the flavor symmetry of a system of free quarks in the ultraviolet. Okay. So one way to think about this theory is that you start in the deep ultraviolet with a system of free quarks, and you turn on a relevant deformation that is gauging a subgroup of the flavor symmetry that triggers an RG flow. Another question that we want to find an answer to is what happens in the infrared. Okay, so let me tell you a couple of preparatory remarks about QCD in 2 dimensions that will help us organize how we're going to search for the gap and gapless theories. If the QCD theory in 2 dimensions has a one-form symmetry, namely the theory has an unscreened center symmetry, the QCD Hilbert space is split into distinct topological sectors that are labeled by the one-form symmetry. This has a very elegant physical interpretation that in some sense goes back to Coleman and Witten, which says that these topological sectors is equivalent to studying QCD in a Poincare invariant background in 2 dimensions, in the background of a flux tube created by probe quarks at infinity. So if you're in the topological sector labeled by rho, which essentially takes values in the value of representations of the one-form symmetry, what this corresponds is studying the theory with a flux tube that was created by a pair of quarks at infinity of rho and rho bar. Okay. Now I'll give you a quick argument to show that it is sufficient to consider, for the questions of whether the theory is gapped or gapless, it is sufficient to study the theory in the zero string sector. And it suffices to study QCD when the gauge group is simply connected. So the main reason is that essentially QCD has certain topological lines that have zero tension and zero energy density that allows you to interpolate by acting on the vacuum. So this kind of picture. You can go from the sector with no flux tube to the sector with a flux tube by acting one of those topological line operators. But these guys carry zero energy density, and that's why the theory will be gapless, if and only if it is gapless or gapped in the zero string sector. And also, just to mention here that it suffices to study the theory with a simply connected gauge group, because if you try to study the theory with a non-simply connected gauge group, so you take a quotient of the simply connected gauge group by a discrete group of the center and with a theta angle, this is exactly the same as studying the theory with a simply connected gauge group in the presence of a non-trivial flux tube, because the theta angles and the flux tubes are labeled exactly by the same data. So the summary of this slide is that for the purposes of classifying gap theories, it will suffice to study the zero string sector, no flux tube in it, and with simply connected gauge groups. Okay, so now we're going to make a couple of preparatory remarks that you can say without getting out of your chair about kind of necessary conditions for theories to be gapless. Okay, so a necessary condition for a QCD theory to be gapped is that it has no tooth anomalies for continuous symmetries. In particular, this means two immediate results, so that a gapped QCD theory cannot have any continuous chiral symmetries, chiral flavor symmetries. If you have a continuous chiral flavor symmetry, and you turn on a background gauge field for that flavor symmetry, that would give rise to a tooth anomaly. And if you have a tooth anomaly for a continuous symmetry, the theory in the infrared is necessarily gapless, because the correlation functions of the currents have to have support at separated points. And this is not something that cannot be afforded by a topological quantum field theory. So it's a gapless theory. Moreover, in 2 dimensions...
is this only true for 2 dimensions, or is it true in general?
It's true in general, in fact.
I see. Okay, thank you.
What's special in two dimensions is that the fact that the theory is gapless, I mean, something special extra you can see in two dimensions is that the theory is gapless, but due to the Coleman-Mermin-Wagner theorem, the vacuum actually will have to be symmetry preserving. You cannot have a spontaneous symmetry breaking by continuous flavor symmetry in two dimensions. So this immediately tells you have a continuous, you have a chiral symmetry. The theory will have to flow to a conformal field theory. Likewise, if the theory has gravitational anomalies, the theory will be gapless because that means you have non-zero correlation functions, the energy momentum tensor at separated points. One thing that's very important in two dimensions compared to four dimensions, that's related to the question that I was just mentioned, is that the nature of the flavor symmetries in two dimensions is very different in four dimensions. In two dimensions, depending whether the representation is real, pseudo-real, or complex, the flavor symmetry of the quarks are different. Okay. So in particular, if you have a quark, so this is essentially what I'm going to say here. So tooth anomalies alone, so without doing any work, constrain the quark quantum of theories that are gapped in two dimensions. So a necessary condition, very far from being sufficient, but a necessary condition for the theory to be gapped is that the quark content of the left and right moving quarks is a direct sum of distinct real representations of the Gates group. If they had been either a complex or a real representation, then there would be a flavor symmetry, and therefore it would be gapless. And the absence of gravitational anomalies that would lead to a gapless theory implies that the dimension of the left, the representation of the left moving quarks and right moving quarks has to be the same. Okay. So this is as far as you can get without really doing any work. But already you can derive some consequences about what properties the theory will have to obey for the theory to be gapped. And this is quite different than in four dimensions, in which, for example, all the flavor symmetries are always unitary. That's not the case in two dimensions.
I'm sorry, I am confused because two-dimensional theories have Coleman theorem, which tell you that there are no massless excitations interacting massless excitations.
No. It says that it says that there's no spontaneous symmetry breaking of continuous symmetries. You of course have two-dimensional massless conformal field theories with symmetry preserving vacuum.
Okay.
I mean, there are two-dimensional conformal field theories in the world.
Yes,
that somebody is definitely correct, is that you don't have Nambu-Wollstone bosons. That's the statement. Okay. Okay, so this is, but now we want to know more than this. We now want to know which theories are actually gapped. We know some necessary conditions, but we'd like to know which ones are actually gapped. So in the rest of the talk, I will mention how to derive necessary and sufficient conditions for the theory to be gapped that follow by looking at both. Actually, yeah, you get the same conditions by studying both the light cone and temporal Hamiltonians of two-dimensional Qcd. So let me just sketch the argument. So for conclusions, I'm going to choose the argument using the light cone Hamiltonian. So in the light cone quantization, you choose one of the light cone coordinates as time and as quantization. And the matter spectrum of the theory is obtained by diagonalizing P plus and P minus. Okay? Now, the non-trivial part of the Hamiltonian in the light cone gates is essentially given by this, P minus, given by this expression. This has a very simple interpretation. This just tells you that you have two charged sources integrating out the Gates field generates an instantaneous Coulomb potential, which is essentially of this form. Okay. Now, what are these J's? JAs are essentially the quark currents that we have gauged to construct the QCD theory, starting from the free quarks in the ultraviolet. And a famous result is that these quark currents in two dimensions generate not only a G flavor symmetry, but actually a GK current algebra, where the level of the current algebra is given by the index, the Dynkin index of the representation of the quarks. Okay. So this light cone Hamiltonian acts on the quark Hilbert space that you create just, and the good thing about the light cone Hamiltonian is essentially the Hilbert space is essentially the Fock space of states. Okay. So just create the modular Fock space by acting on the vacuum with the creation operators. I'm skipping all kinds of details that, I mean, this is an old story about light cone quantization. Okay. Now, studying at the Hamiltonian here, you can immediately derive the necessary and sufficient conditions for a state to be massless. Okay. So if you look at this statement at the Hamiltonian, you find that there are two conditions. The first condition is that the state has to be a primary state of the current algebra. That's essentially the statement that the states are annihilated by Jm with positive n. That's essentially the definition of what a primary operator is, or a primary state is in a current algebra. And the other one is to remember that after we have fixed the light-cone gates, we still have residual gauge transformations. So the state in the Hilbert space has to be a gauge singlet. Another way of saying it is it has to transform the trivial representation of the gauge group G. Okay. So therefore QCD is gap even only if the vacuum is the unique state which is a primary and singlet in the Hilbert space. If there was any other state in the Hilbert space which was primary and singlet, it would lead to a massless particle. So let's unpack this a little bit. How are we going to use this description to actually give a complete classification of the gap theories? So now we have to discuss the Hilbert space that's created by the quarks. It is useful to use the fact that the Hilbert space of quarks can be written as modules of a orthogonal current algebra at level 1. That goes back to all ideas of Witten. Okay. Now, what are we doing when we construct the QCD theory? What we do is gauging a subgroup of the flavor symmetry. That's what the QCD theory is gauging a certain subgroup of the flavor symmetry, and this induces an embedding of current algebras. So remember that I said that the quark currents generate a current algebra, and this embedding of the gauge group into the flavor symmetry of the fermions induces an embedding of the current algebras. Okay. Now, essentially, what we want to do is we want to study the Fock space, the Hilbert space of the free fermions, and decompose it into representations of the the current algebra G at level K. Okay. This is a close analog of what you do in representation theory when you decompose representation in the subgroups. Except that now this is more subtle because we're dealing with current algebras. So essentially, what we do is we take the characters of the SO current algebra and decompose it into the characters of the G level IR current algebra. And there are these interesting coefficients here that essentially, okay, I'm going to tell you what they measure. Okay, essentially, this function B counts the primary states of the G current algebra that you have gauged that are in the module of the SO current algebra. Okay. And essentially, that's exactly the object we want to find out. We want to know if in the Hilbert space there are primary states of G that are singlet. So we'll have to get there. Okay. And B has a beautiful interpretation. This function here, this is a non-trivial function because these characters are complicated objects. Is essentially the character of the commutant chiral algebra, and which in particular will contain the difference of the energy momentum tensor of the free quarks in the ultraviolet minus the energy momentum tensor of the gauged currents. Okay. And if you have a flavor symmetry, it will involve some flavor symmetry current algebra. Okay. So now let's go back to the condition that we're trying to solve for. QCD is gap if and only if the vacuum state is the unique primary singlet state in the Hilbert space. In the language that I just described, this is exactly the same as the following, as demanding that in terms of the branching functions, implies that QCD is gap even only if the branching functions from any module of SO to the trivial representation is independent of Q. If it depended on Q, it would mean that there are extra states other than the vacuum that are singlet and primary, and that would lead to a gapless condition. So now let's consider first the decomposition, the branching function from the trivial representation of SO into the trivial representation of G. So this has this canonical expansion up to a factor that we're not going to discuss. It's canonical. It has to do with the central charge of the free fermions and the gauge theory. The existence of this one here is a statement that you have the vacuum state. So of course there should be a vacuum state. The vacuum state is G invariant. Okay. Now let's study and this, by the way, so this function has an infinite power series in powers of Q, and we need that all Q dependence other than this overall trivial one is trivial. So there is only this coefficient one. Okay, that will guarantee that the theory is gapped. So let's look at this A1. A1 has a simple interpretation. A1 essentially is the dimension of the flavor symmetry group of your theory, okay? So an necessary condition to get a gap spectrum is that there is no flavor symmetry. There are no continuous global symmetries. And this is the Hamiltonian way of rederiving what I had already argued before using Tooth anomalies, okay? So we have seen explicitly from the form of the Hamiltonian that the theory can, in order for it to be gapped, it cannot have any continuous global symmetries. And you can think of this contribution to the power of Q as a state created by acting with J-1 alpha acting on the vacuum, which of course commutes with the Hamiltonian if it's a flavor symmetry. Because the flavor symmetry at the Hamiltonian is constructed of the Gibbs currents, which commute with the flavor symmetries. Good. Now let's look at the Q squared term, which will essentially, the constraint that will come from it will be so strong that will allow us to completely solve to answer this question. So now we want to look at what this Q squared term is. It's easy to show that A2, if there are no flavor symmetries, this A2 coefficient is 1, okay? And actually the state at level Q squared is a very particular combination of the quark operators, which is precisely, you can show that it's precisely the difference of the energy momentum tensor of the free quarks in the ultraviolet minus the energy momentum tensor of the Gibbs current. So that's called the Sugawara energy momentum tensor, okay? So this state creates, so if this operator exists, if this operator is non-trivial, then this operator creates massless particles. So the existence of a gap spectrum requires that actually this operator is 0, namely that T of the ultraviolet quarks is the same as T of the Gibbs currents, okay? And actually this condition itself actually implies something much stronger. You don't have to check anything else. If this condition is satisfied, all of these will be true, and B will just be a constant independent of Q, okay? So therefore, what I have discussed here is that the necessary unconservation conditions for a QCD theory to be gapped is that this equation is obeyed, that the ultraviolet canonical energy momentum tensor is the same as the Sugawara energy momentum tensor for the Gibbs current. Now this equation, now you have to unpack it. This equation looks a bit strange because TSO is quadratic in the fermions, while TG is nominally quartic in the fermions because the quark currents are quadratic in the fermions. But you have to remember these are normal order of equations that you need to study. Now, let me mention that here, an object that will appear momentarily is...
In principle, you are more or less out of time, so you can, if you want some time for questions, it will be good.
Okay. So essentially, I'll just finish with this part, and if people want, I can discuss some things that I didn't really have that much time to discuss. Essentially, solving this equation implies that these T matrices, that essentially are the matrices that tell you under which representation the quarks transform, has to satisfy a Jacobi-like identity. It turns out that the solution of these equations are in one-to-one correspondence with the classification of symmetric spaces by Cartan. Okay? So therefore, since this is a complete classification, we can give a complete list of QCD theories that are gapped, and any other theory that is not in that list will be gapped. So let me just show you what the list is very quickly. So this is the complete list of all QCD theories that are gapped. Let me tell you just a couple of quick things. So the main thing that to notice is that for the classical groups, what you find is that all the representations that appear essentially are either at most rank 2. Anything that has a quark with a representation higher than rank 2 is gapless. And then you see that there is some exceptional theories that are also gapped. I was going to say something about, okay, if you want later on, so let me just finish. If you want, you can ask me what is the proposed infrared dynamic of these theories and how to study various properties of various flows. So let me just conclude. So QCD in 2 dimensions exhibit interesting phenomena, including non-perturbative condensates, quasi confinement, non-trivial RG flows that I didn't really have time to discuss. Now, the problem of determining which theories are gapped in 2 dimensions can be completely solved, and it is a exhaustive list of all cases that are gapped. Okay. Now, we can use the mapping between the operators in the deep ultraviolet and the deep infrared to study deformations of QCD by various interesting operators that you can add to a Lagrangian in ultraviolet and see what their effect is in the infrared. Okay? So just to conclude more philosophically is that we have seen that Hamiltonian methods have been extremely fruitful to study this question of which QCD theories are gapped in 1+1 dimensions. And it would be interesting to see to what extent this can be extended to 3 dimensions, in which Feynman, Caravali, and Lanier had made already some attempts in trying to study this problem using Hamiltonian methods in 3 dimensions. So with that, I'll stop. I'm sorry for going a little bit over time.
It's okay. You were right on time. Let's thank Jaume. So we have time for questions. I have one very naive question. Why did I thought that in this truncation method people always have to worry about normalization, and it looks like you only put some 2 dots, and you never discussed counter terms or all this mess that normally appears when people do.
Hamiltonian truncation and light quantization is not the same thing. The DRCQ is not the same thing, as far as I know. And by the way, the theory is super renormalizable. QCD is mega renormalizable in 2 dimensions. So the issue of counter terms is extremely tame. There are extremely few UV divergences. So no.
I see. And just one. Are some of these gap theories integrable?
Yeah. So these are something I didn't really quite discuss. No. So the gap theories are. Okay, so the thing that you can ask is, I think that the more relevant question is actually it's related to this, if you wish, to this question here. So you can consider, for example, a particular QCD theory. So let me tell you in what context you can get integrable theories. So look at this particular gauge theory. Take a spin 7 gauge theory with a quark in the spin representation of SO8. Well, we can argue that this theory flows to the Ising conformal field theory. Okay? Now you can ask the following question, and we can, in a part that they didn't discuss in detail, we can construct the mapping of all operators in this QCD theory with operators in the Ising CFT. Of course, many of them decouple, but not all of them decouple. So now one thing you can try to ask is, imagine now I deform this theory by adding a mass term. Now, since we know the operator mapping, we know what the deformation, but a small deformation, giving a small mass to the quarks here corresponds to giving our operator mapping, corresponds to adding to the Ising CFT a small sigma operator. This is the famous E8 integrable theory of Zamolodchikov, okay? So in this way, you can get the integrable E8 theory emerges by studying with spin 7 with quarks, where you're giving a small mass. Notice that it is interesting that the integrable E8 theory has 8 massive particles, famously. And notice that this 8 is not, I mean, I don't know how to make it super precise, but these 8 massive particles are precisely the 8 quarks that you get here in the ultraviolet gauge theory. So yes, so by studying, so if you're in the massless theory, you're going to get either a CFT or a topological quantum field theory, but then you can study deformations induced by either mass terms or relevant quartic operators relevant 4 Fermi quartic 4 Fermi operators you can have in 2 dimensions, which are relevant in 4 dimensions.
Ah, very nice. Okay, I'll ask more about this 8 later. But okay, let's move on. Get it, Ramon?
Yes, hello. Very nice talk.
Thank you.
With the light cone Hamiltonian approach that you show us, there is an additional assumption, indeed, which is the periodic boundary conditions you need to compute your eigenstates, because otherwise you have 0 modes.
Yes.
So that's a very delicate problem, indeed.
Yes.
So, what can you tell us about this?
Yeah, so that's an extremely good question. And actually, I think, well, so the first thing to say is that exactly the same condition, I don't know which is into that. Exactly the same condition here that I derived using the light cone Hamiltonian can be derived using the temporal gauge Hamiltonian. Now, the temporal gauge Hamiltonian is not as useful to do numerics because you don't have this nice discretization, as natural discretization in the light cone gauge. But it's totally true that the DLCQ has several conceptual issues that one has to deal with. One is that you can get fermion zero modes, but also you can get gauge field zero modes. And that's why, in part, the computation, as far as I know, people, for example, have not studied the spectrum of QCD in the presence of a flux tube using DLCQ precisely because you don't really know how to deal with the zero modes. Exactly. But for the purposes of classifying Kaplan theories, I can be in the zero flux tube sector as I showed, and go through. But as I said, this operator equation, it's the same. The condition is the same in DLCQ and temporal gauge. But I agree that and I think some of the issues of DLCQ zero modes can be done better than they should have been done, as far as I know. I don't know all the literature, but certainly there are issues with the flux tube. I think flux tubes could be incorporated into the LCQ by detecting the zero modes properly.
Yeah, that's a very interesting problem. Thank you. Thank you very much.
Thank you.
Lance?
Hi, thanks for a nice talk.
Thank you.
Two quick questions. One is about the logic that is on this slide about the arrow that says you only need to check the first two coefficients and then you get the rest for free.
Yeah.
And the second was whether in your classification of the gap theories you allowed for reducible representations.
Yeah, of course. Okay. Yeah. No. So the second one is
yeah. Okay.
So in the list here, in the list here, definitely I allow the most general reducible representations. Yes. Now, of course, you can do silly things. You can add direct sums of decoupled theories. I don't think you want that, but in the classification,
I meant
I allow
reducible for not for the gauge group so much, but for R. You would have an antisymmetric tensor plus a fundamental or something like that. Could you do that?
Yeah, I allow that. No, this is the objectives list.
Okay, so those just don't ever become.
Yeah, those are gapless.
Thanks. And how about the logic of how you argue for?
Oh, so this is a bit technical. Let me try to remember. Let me see. So
you have to use modular properties or something like
that.
Yes.
It's essentially comparing dimensions.
Okay.
By comparing dimensions, so essentially you have a Q expansion on the left and the right. It follows essentially from that this function is this. I mean, it's a technical thing. But it's completely straightforward. Yeah.
I suggest that we continue asking questions either during lunch or during the discussion, but so far we managed to stay on time, so let's thank Jaume once more. And